We had looked into two kinds of crystal structures so far. The body-centered cubic crystal structure, which is known as BCC, and we have also looked into the FCC crystal structure, which is face-centered cubic crystal structure. Both of these crystal structures, they are being normally followed by metallic system. Some of the metallic systems, they follow this hexagonal closed pack, which is known as HCP crystal structure. So we'll be looking into how this crystal structure looks like and how are the atoms positioned in this crystal structure. Uh, it says that not all metals have unit cells with cubic symmetry, as I had already mentioned. The last of the common metallic crystal structure has a unit cell which is known as hexagonal closed pack or HCP crystal structure. In this crystal structure, you essentially have an hexagon as shown in the image to the right. There are two basal planes. This plane, the hexagonal plane, this is the top hexagonal plane, and this is the bottom hexagonal plane. Now, in top and bottom hexagonal plane, they are exactly similar. What is happening in a hexagonal plane or the basal planes is that if you have a hexagon like this, kindly bear with my drawing skills. So you have essentially 1, 2, 3, 4, 5, and 6. There are 6 corner atoms in a basal plane of a hexagon which surrounds a central atom in the center. This is the basal plane of an hexagon. You have a similar basal plane at the bottom. I'm not going to draw it completely as it is already drawn for you, but you have uh, a similar basal plane at the bottom. Is this clear to you?
Yes, sir.
That's okay.
All right. All right. Now, other than this, you have 3 more atoms which are situated within the body of the hexagon, and it is situated in a plane. It is a plane which is essentially situated in the center of the two planes, the top plane and the bottom plane. There is a plane which is in the center of the hexagon, and within this plane there are 3 other atoms which are situated within this hexagonal crystal structure. Is this clear?
Yes, sir.
Is all right. So as it says, the top and bottom faces of the unit cell consist of 6 atoms that form regular hexagons, and they surround a single atom which is situated in the center of the hexagonal plane. Other than that, there is another plane that provides 3 additional atoms to the unit cell which are situated between the top and bottom planes, exactly in between. The metals that follow this crystal structure, uh, they are basically cadmium, magnesium, titanium, zinc. They are the metallic elements, or they are the materials that follow this hexagonal closed packed crystal structure. Now, if you remember the cubic system, whether it's BCC or FCC. If I have to draw the cubic system to the accurate dimensions, what information do I need to have?
Sir, its length?
Sir, length
Length,
of side. Sir,
yes,
length of.
length of one side, which is known as lattice parameter. I repeat this word over and over again so that you associate the lattice parameter with the geometry of your crystal system or crystal structure. Clear? So the geometric representation of your crystal structure is being defined by lattice parameter or parameters. When I say cube, the only lattice parameter that I need to know is known as A, one of the side length of the cube. So if I am familiar or if I am aware of the lattice parameter A for a cubic geometry, I can essentially draw that crystal structure to greatest accuracy. Clear enough?
Yes, sir, clear.
All right. However, in case of a hexagon, uh, you need to know more than one lattice parameter in order to draw the hexagonal crystal structure. The basal plane, all the lengths in the basal plane, they are represented by A. Since it's a hexagon and all the sides are equal, so if you know any one of the length, you can essentially draw the hexagon. Uh, this is one of the lattice parameter that you need to know. But the problem comes that you have to define the height of the hexagonal crystal structure in order to geometrically draw it or represent it. So another lattice parameter for hexagonal crystal structure is basically defined by C, which defines its uh, elongation or depth along the z-axis. So from the basal plane, the height of the hexagon is basically defined by the lattice parameter, which is termed as C. So in order for hexagonal crystal structure, you need to have the information about the lattice parameters A and C. Clear enough? So far, is it clear?
Yes,
Yes,
sir.
sir.
All right.
Yes, sir.
But all right. But the important thing is, in this case also, if you are familiar with the lattice parameter A, the information is sufficient enough for you to draw the hexagonal crystal structure. Why? Because the ratio of C to A, the longitudinal direction to the basal direction, the edge length to the height of the hexagon, is defined as 1.633. Now, this since the ratio is fixed, the only thing that would change would be the exact values of A and C. So if you are familiar with the A value for cadmium, you can essentially find out the depth of cadmium itself. Similarly, if you are familiar with the A value for magnesium, you can find out the C value for magnesium. So essentially, in hexagonal crystal structures, with this information known to you can essentially draw the hexagonal crystal structure if you are familiar with the lattice parameter A. I hope this is clear to you.
Yes, sir.
Right. Now, the important thing comes that a total of how many atoms are assigned to an HCP unit cell, hexagonal closed packed crystal structure. A total of how many atoms are associated with HCP unit cell. Like you saw in FCC unit cell, there are altogether 4 atoms that completely belong to a single unit cell, and in BCC, there are altogether of 2 atoms that belong to the complete single unit of a BCC crystal structure or BCC unit cell. In case of HCP, now before we move on how to find out the total number of atoms, let's uh, identify the common atoms having common characteristics. So I'll divide these atoms into 3 categories. One is the atom which is at the corner of your edges or edge corner. The other atoms are situated or are known as face-centered atoms, and these 3 atoms, they are characterized as body-centered atoms. If I ask you about the edge-centered atoms, what is the contribution of an atom which is situated at the center of an edge sorry, at the corner of an edge, uh, what is the contribution of the edge corner atom towards the HCP crystal structure?
Sir, 3.
So 6.
All right, I have got one answer as 3 and the other answer as 6. Let's see. G.
1/6, sir.
All right, some say 1/6. All right, that I understood. Okay, so let's say that this is your hexagon, somewhat. The hexagons which would be situated now, I'm drawing this plane only right now. So the or I am drawing the upper plane in other words. So there is a depth in the. I'm just drawing it without the depth. So this is the hexagon. There would be another hexagon which would be situated next to it, the neighboring hexagon. And this would be another hexagon that would be situated next to the this hexagon. So let's say I'm talking about this corner atom. This corner atom is being shared by how many unit cells?
3 sir.
Sir 6.
Yes,
सर
it
ऊपर भी
would
आ जाएगा ना
मतलब नीचे
same?
नीचे 3 है, ऊपर जब आप डालेंगे तो 6 हो जाएगा.
बिल्कुल, exactly. So these are 3 and there would be it would be shared by the hexagons which are on top of it. So essentially this single atom is essentially shared by 6 unit cells of hexagonal cross pack crystal structure. Clear? Anybody who has doubt in this? किसी को डाउट इस चीज में?
No, sir.
No,
All right.
sir.
All right. So the contribution of a HCP crystal structure, the corner edge atom towards the HCP unit cell would be 1/6. Similarly, if I talk about the face-centered atom, which is this atom, what is the contribution of this atom towards the unit cell?
Sir 1/2.
Yes, it is being shared by 2 unit cells, so the contribution would be 1/2. One unit cell is itself in which the atom is being shown to you, and the other unit cell is on top of it. So this single atom is being shared by 2 unit cells. Similarly, the body-centered atoms, the contribution of a single body-centered atom in an HCP unit cell is what? It is being
One,
shared
sir.
by how many? It's being shared by one
One
unit
unit.
cell, and the contribution would also be 1. So altogether, how many edge corner atoms are there?
Excuse me, sir.
G.
सर बॉडी सेंटर्ड का दोबारा बताइएगा. सर ये 1 किस तरह है?
बॉडी सेंटर्ड का कंट्रीब्यूशन क्या है? ये एक अगर लेट्स से sorry, let's say I take this single atom, ये कितने यूनिट सेल्स में शेयर हो रहा है?
सर हेयर 1.
एक में शेयर हो रहा है ना, तो ये एक यूनिट सेल में शेयर हो रहा है, इसका कंट्रीब्यूशन भी एक ही होगा, यूनिट सेल की तरफ ही होगा, कंप्लीटली यूनिट सेल को बिलोंग करता है. क्लियर?
ओके सर.
ऑलराइट. सो हाउ मेनी एज कॉर्नर एटम्स आर देयर?
12 sir.
12. So their total contribution would become 2 atoms. All right. How many face-centered atoms are there?
2 sir.
So their contribution would become 2, and there are essentially 3 atoms which are within the body of this hexagonal crystal structure. So altogether, the total number of atoms that belong to the HCP crystal structure would then become 6. Clear enough?
Yes, sir.
All right. Moving on, we have to find out the atomic packing factor for the HCP crystal structure. Atomic packing factor, as I had mentioned earlier, is the volume of atoms in the unit cell divided by the total unit cell volume. It gives you an indication that how much occupied is your unit cell, or how closely packed the atoms are there within this crystal structure. Before we look into how to calculate the crystal, uh, atomic packing factor, I'll give you the value of atomic packing factor for HCP, which is 0.74. This is the same level of densification as it was there in FCC crystal structure. So FCC and HCP crystal structures, they are the closely packed crystal structures in metallic systems. Now, moving on, how to find out the atomic packing factor. For HCP, you know that there are equivalent of 6 spheres or atoms per unit cell. So the volume of atoms that belong to a single unit cell would essentially be number of atoms, which is 6, multiplied by the volume of an individual atom, which is 4 pi r cube divided by 3, or 4 over 3 pi r cube, which is the volume of the sphere. This comes out to be 8 pi r cube. Clear enough? Is it clear? Yes,
Yes,
no?
sir.
Yes, sir. Yes, sir.
Yes, sir.
All right, all right. Please respond me back so that I know I can go ahead conveniently. Anyways, now the second thing is to find out the total unit cell volume. All right, if I say that in order to find out the unit cell volume, I first find out the area of the base, the basal area, and multiply it with my height. That would give me the volume. So volume is equals to base area multiplied by the height, which is represented by C. Do you agree with this?
Yes, sir.
All right, if you
Yes.
agree, let's move on and try to understand how can we find out the basal area. So as it says that the unit cell volume is the product of the base area multiplied by the cell height, which is C. Let's try to find out the basal area. This is essentially the basal area where you have 1, 2, 3, 4, 5, 6 corner atoms which are surrounding the face centered atom. All right. Now, if I define what is the length ED?
A, sir.
Sir,
A.
yeah.
Very good. All these lengths are essentially A. And if I say that this is R and this is R, so essentially A is equivalent to 2R. Would you agree with this or not?
Yes,
Yes,
sir.
sir.
All right. Now let us look at the triangle OAB. We know that the length AB is essentially A, which is equivalent to 2R. Do you agree that the length OA is also equivalent to 2R, or essentially equivalent to A?
Yes, sir.
Yes, sir.
Similarly, the length OB is equivalent to 2R or is equivalent to A.
Yes, sir.
Now, now, if we have all the three lengths of the triangle equal to A, we essentially have an equilateral triangle where the internal angle is essentially 60 degrees. So if I take this triangle out, I would essentially have a triangle OAB where the length AB is essentially A and the interior angle is 60 degrees. If I want to find out the area of this triangle, the simplest relationship that I know is that half into base into height. Half into base is essentially A. And if I look at this height, it is essentially A sine of 60 degrees. This is my A hypotenuse. This is the right angle. Now this height in front of it would be A sine of 60. So the area of this triangle would be A half A into A sine 60, which is under root 3 over 4 A square. Agreed?
सर
Yes,
ये
sir.
एक बार रिपीट कर
Yes,
दीजिए
जी
लास्ट
सॉरी
सर ये एक दफा रिपीट कर दीजिए ये 1 ओवर b into l 1 over 2 b into l ये वाला
1 over 2 p
1
into
over
n.
यस सर ये किस तरह सर a sin 60 और सर ये समझिए
आपको ये पता है ये लेंथ ए बी यहाँ पे क्या लिखी हुई है? आई हैव टेकन आउट दिस
यस सर
ट्राइंगल.
सर ये इक्विलेटरल ट्रायंगल a है सर लेंथ सब
ठीक हो गया. नाउ लेट्स टेक दिस ट्राइंगल आउट. सो आई हैव अ ट्राइंगल जिसमें ओ ए लेंथ क्या है?
a है
So 2R.
और ए एंगल क्या है?
सर 60 डिग्री
60.
60 डिग्री. तो साइन ऑफ 60, व्हाट इज साइन ऑफ 60?
सर 1 over 2 I think so
Sir, under root 3 by 2, sir. Under root 3 by 2.
I am not asking in a right angle triangle. If you have a right angle triangle, what is sine of 60? It is the opposite
Sir, under
length.
root 3 by 2.
I know that. I'm not asking for the numerical value. I am asking for the relationship.
सर
Let's
perpendicular
say,
over hypotenuse
so it is essentially x upon a,
yes sir
और x से मैं height लिख दूं, so h upon a. So h is essentially a sine of 60. Clear?
yes sir
So
ठीक
this length is essentially a sine of 60. Now if you have to find out the area of the triangle, it is half multiplied by base, which is a, multiplied by the height, which is a sine of 60. So half into a multiplied by a sine of 60 would give you under root 3 over 4 a square. Clear enough?
yes sir clear
All right. So now we know the area of a single triangle. This area is known to us. How many of such triangles are there in the base?
6, sir.
6.
Essentially, there are 6 triangles having the same area. So the area of the basal plane would essentially be 6 multiplied by the area of a single triangle, which is under root 3 over 4a square. This would become 3 under root 3 over 2a square. Clear enough?
yes sir
Yes, sir.
All right.
Yes, sir. Yes, sir.
Remember this volume of the atoms. Anyways, moving on. So this is the area of the basal plane, which is in terms of A. I already have developed a relationship that A is essentially equal to 2 times R. Known to me?
Yes, sir.
Yes, sir.
Yes,
A
sir.
square would be equal to 4R square. So if I replace this A square with 4R square, essentially I would have the basal area as 6R square under root 3 in terms of R. Clear?
Yes, sir, got that.
Yes, sir.
Yes, sir. Yes, sir.
Now you know that C over A, as I had defined earlier, is 1.63. The ratio is 1.63. So C is essentially equal to 1.63 times A or 3.26 times R, since A is equivalent to 2R. Now, once I have this relationship for C, the volume of the unit cell is essentially basal area multiplied by C or basal area multiplied by 3.26 R. So C is replaced by 3.26 R and the basal area 6 under root 3 comes out to be 10.392 R square, which makes up the total volume of the unit cell as 33.878 R cube. Clear enough?
Yes, sir.
Yes, sir.
Yes, sir.
Atomic packing factor is volume of atoms divided by the volume of unit cell. So volume of atoms is 8 pi r cube, volume of unit cell is 33.878 r cube would essentially cancel out, and if you find out the ratio it comes out to be 0.74, which means 74% of the unit cell volume is being occupied by the atoms. The remaining 26% is essentially the empty space or the voids. All right.
ठीक है सर.
All right. Moving on towards the coordination number. How do you find out the coordination number for an HCP crystal structure? Now, in order to find out the coordination number, I'll show you the arrangement of atoms. The coordination number for HCP is 12. We'll try to understand how is it possible. Let's first look at this layer, which is known as the basal layer, the arrangement of atoms in this basal layer. So in this basal layer, you have one, two, three, four, five, six corner atoms, and then there is a face centered atom. Now, if you look, this is the basal layer or basal plane. If you look at this arrangement of atoms, you would identify there are two different kind of cavities. The cavities, if I identify for you, one kind of cavity is this cavity, in which the vertex is upwards. You have the same kind of cavity over here. Again, the vertex is upwards. Similarly, you have another cavity of the same kind in which the vertex is facing upwards. This is one kind of the cavity that exists between the atoms which are closely packed in basal plane. The other kind of cavity is essentially the vertex which is faced downwards. So you have three cavities which are facing upwards and three cavities which are facing downwards. All right.
Yes, sir.
These cavities are essentially known as trigonal holes or trigonal voids. Now, you know that the second layer, which is the middle layer, uh, the middle layer of atoms, which is this layer, this would come on top of the basal layer. Now, in order for the atoms to come on top of this basal layer, the three atoms would have to decide for themselves whether they are going to occupy the cavity where the vertex is facing downwards or the cavity where the vertex is facing upwards. So the cavities would have to define for themselves. Let's say the cavities, the atoms decide, the three atoms decide that they would occupy this cavity. So the three atoms would essentially occupy the same nature of cavities. Clear enough?
Yes, sir.
So if you see over here, the next layer, which is the middle layer, this cavity, the facing upward cavity, this cavity which is facing upward cavity, and this cavity which is facing upward cavity, atoms have not occupied that space. They have occupied a space in which the cavities are facing downwards, or trigonal holes in which the vertex is facing downwards. Now, if I look at the basal layer, this central atom, in the basal layer, how many atoms are in contact with this atom in the basal layer?
The question repeat here.
How many atoms are there in contact with this central atom in the basal layer?
So 9 atoms.
Sir, 9.
Within this basal layer, how many atoms? Are there 9 atoms in this layer?
So 6.
Sir 12 नहीं होगा?
Sir, 6.
I am referring to the basal
ठीक है, हाँ,
layer.
6 हो गया,
Please
6.
listen carefully.
Sir, 6.
6 sir.
There would be altogether 6 atoms, 1, 2, 3, 4, 5, and 6 atoms that are in contact with the central atom in the basal layer. Clear enough?
Yes, sir.
Yes, sir.
Now, when the middle layer comes on top of this basal layer, that means atoms occupy this cavities, which is shown over here. So the middle layer, these 3 atoms, are they in contact with the central atom in the basal layer?
Yes, sir.
So essentially, with this basal layer, with this middle layer on top of the basal layer, you essentially have 9 atoms that are in contact with the central atom. Clear enough?
Yes, sir.
Yes, sir.
And you would have an exactly same arrangement of atoms beneath this layer, basal layer. These atoms have come on top of the basal layer. There would be a set of atoms which would be there behind the basal layer or beneath the basal layer. So this atom, this is the basal, this is the middle layer on top of it. Then there would be another layer of atoms that would be there beneath this basal layer, just like it is shown over here. So you would have 3 atoms on top of this, 3 atoms beneath this basal layer, making altogether how many atoms in contact with the central atom?
Sir, 12.
Sir, 12.
12. So therefore the coordination number for an HCP crystal structure is 12, which is common with that of FCC. This again shows you that they would have the same atomic packing factor. Clear?
Yes, sir.
Yes, sir.
Moving on, how do you find the density of a material? Now, I hope you would have heard about the Archimedes principle in your high school physics.
Yes, sir.
All right. If you want to find out the density of a material, there is a way based on Archimedes principle that you could experimentally find out the density of a material. But if you want to find out or compute the density of a material theoretically, here is the relationship. The theoretical density of a material could be found out using the information about the crystal structure. That means how many atoms are there within the unit cell, the atomic weight of the material, the volume of the unit cell, and the Avogadro's number. We have an example over here which says that copper, again element, which has an atomic radius of 0.128 nanometers, having FCC crystal structure, atomic weight of 63.5, you have to compute the theoretical density of copper, having known that the measured or the experimental density is 8.49 grams per centimeter cube. So what we'll do is that we'll find out the density theoretically. Let's say we look into this computation first, N multiplied by A. In an FCC unit cell, there are essentially 4 atoms in a unit cell. 4 atoms in a unit cell multiplied by the atomic weight of the copper, which is 63.5 grams per mole. This makes the product makes it 254 atoms grams unit cell multiplied by mole. In order to find out the volume of the unit cell, let's say the volume of unit cell VC for an FCC is A cube. A is essentially equal to 2 under root 2 R whole cube. This would become essentially 16 under root 2 R cube, and R is given to you as 0.128 nanometers. Since we are having the density in grams per centimeter cube, I would use the value of R in terms of centimeter. So this would be 0.128 into 10 raised to power minus 7 centimeter whole cube. This value would essentially come out to be 4.745 into 10 raised to power minus 23 centimeter cube per unit cell. So this is the volume of a single unit cell of FCC copper. And Avogadro's number you already know is given to you as 6.022 into 10 raised to power 23 atoms per mole. So if I multiply the volume of unit cell by Avogadro's number, the value of both are known, I would have the answer as so this would come out to be 28.574, and you could have the units as atoms centimeter cube divided by unit cell multiplied by mole. Now if you divide this 254 divided by 28.574, and all the rest of the units would cancel out except for grams per centimeter cube, you would have the value of 8.888 grams per centimeter cube, which is essentially equal to 8.89 grams per centimeter cube. So this is how you could find out the theoretical density for a material for which the crystal structure information is known to you, and you could compare it with the experimental density. All right, is this clear to you guys?